Alright, time for another DraftPhysics.com, DebatePhysics.com also, a video presentation. So there's a couple of comments here by, whoa, there was a couple of comments. I really didn't press on that, liars. Anyway, this AleksiSalla, yeah, Salla? Okay, whatever. Comments, and he has a couple of snarky, rude, nasty, stupid comments on the Brozos video. I believe I saw some kind of crap. They're all crap, really. Anyway, so it's unfortunate that none, absolutely zero, of the people who are contending I'm wrong can't draw formal diagrams, that don't really have to be all that formal, explaining what they believe and why they believe it. Where it was proven, that, for example, momentum is a vector and kinetic energy is somehow a scalar, or where they discovered that. What experiment discovered that truth? Some kind of crap like that. Anyway, so anyways, he has answered my questions. I haven't read his answers yet, just because I fear they'll be entertaining. It'd be entertaining for me to read them. And he has proposed a couple other comments here that are just wrong, and I'll just point that out. But it is unfortunate that he's attempting to engage in the argument, but he's engaging it with a bunch of false notions. All right, so he says, so are you saying that two pendulums with the same length and different masses won't oscillate with the same frequency? No, I'm saying exactly the opposite. I'm saying conservation of momentum. And yes, when you use gravity, to create a force, it can only create the force with the mass you're using in the gravitational circumstance. So, it's going to see the mass. It's not going to see the weight. Anyway, according to conventional physics, the masses make no difference. Yeah, that's true. Because the falling speed is the same for all objects, and all you're doing is changing the falling speed. All right, and that's your extra force, is the extra time the object will be in the gravity. The extra time it's in the gravity will be compensated for because of extra friction or extra something else, but the fact is it won't collect its energy if you're making it go slower. The object itself isn't collecting the energy, something else must be. It's friction, essentially. If you make something fall slower than its free fall speed, you have to be applying friction of some kind. The friction is consuming the energy. So whatever it is that's on the other side of the experiment causing the friction has to have the energy that the gravity is producing. While the object is 9.8 meters per second. If the thing isn't moving 9.8 meters per second but still moving, then you know that the extra, the 9.8 this thing isn't getting, has to be going somewhere. It would be easy to test it. So again, it's not my argument. I don't know how you perverted anything I said into a contention that momentum isn't conserved in pendulums, or that gravity is something other than exactly a consistent force, in the sense that depending on your mass, you'll collect more, and if you're lighter, you'll collect less. And when you hit the ground, you'll have less impact. And it is based on a pretty direct relationship to velocity. Twice the velocity, same mass, twice the potential to move matter. Not 4 times the potential. And Google spring potential energy. So I did this. So it's a waste of my time because there was nothing there. So it's too bad you can't just link to a reference. There you can see where the 4 times the energy and twice the compression comes from in conventional physics. Well, I don't know, where does that say anything? These are just bad formalizations. Just like MGH is a bad formalization. When they do the speed conversion, the kinetic energy in, kinetic energy out, they change the formula to V equals the square root of. Well, they're just undoing the square because the square isn't going to be proportional to the velocity. It's going to claim that twice the velocity is twice the energy, which it's not. So, I mean, bad formulas are not a proof of anything. So, not very useful. All right, then he says, so this is his explanation for the problem of the fact that the lever, I tilt it. It has the same mass and the same location on both sides. I tilt it. This mass is actually getting less gravitational energy than this mass. This one's closer to the Earth. This one is, in fact, technically heavier. This one down here is heavier than this one. It is, in fact, closer to the surface of the Earth, closer to the maximum amount of gravity you can be in. This one is closer. The higher I go up, the less weight the object has. That's the paradox. Why does the lever go this way when this is the heavy side? And it has to do with the center of mass is what I'm arguing. Is the fact is the weight, as you rotate it, becomes further and closer to the fulcrum in terms of the amount of mass, amount of lever and mass. And that's the differential that the lever is correcting for. So even though this is lighter, its position to the fulcrum is closer, which means it's moving the center of mass of the lever, which makes this possible, that it tilts the wrong way. And I'm going to argue that this doesn't have anything to do with it, but whatever. All right. The reason the empty lever balances over the fulcrum oscillates, balanced over a fulcrum oscillates, is that in the real world the fulcrum is not a point in space but a three-dimensional object. So a point in space is a three-dimensional object, but regardless, it doesn't matter. We're not talking about any dimensions here. There's only two dimensions involved. This isn't about some other dimensional problem. It's more like a ball. It says you. It's atoms, and the atoms are made out of electrons, and it's the electrons that are pushing on each other that are conveying the information about the fact that something's going on. I mean, the fact that there is a force pushing some stuff, and it's pushing it into the fulcrum, and the fulcrum is tied to a bigger thing that can't move, and that's why something's going to happen. Anyway, ball, and it's more like a ball. If you balance a stick over a ball and push one side of the stick down, this is a lever, frankly, okay, you will see that the area in contact between the stick and the ball moves. Says you. I don't really see that. I can't see it, can't really understand what you're talking about. It'll work just fine on top of a ball. It is now closer to the end that pushed down. Well, what if it pushes up? I don't think there's any paradox on here. So again, going on here. So again, it's not an explanation. I'm just saying that it's just as a practical fact. You just can't deny the fact that this end in the up position, we have this intuition that says, hey, it's heavier. I've lifted it up. It's not heavier. It's lighter. So certainly lighter than the same mass on this other side. So your explanation has to explain how the same mass on both sides, and you have to explain how the side that technically has more mass, and it does have more mass, even if I tilt this, you know, and I keep this position, you can see that this line goes straight through here, all right, which means this side is actually getting heavier. There's actually more lever on that side of the straight line. You know, if I tilt that, you can see this side got bigger. You know, especially if I tilt it from the bottom, you can see that this side is bigger than this side. So I'm just saying, your explanation doesn't explain. So, sorry, no sale. All right, so here he attempts, apparently, to answer some of my previous questions. So this should be worth some conversation. It's a lot of crap there. But we should be able to get through it. Let me try to answer some of these. I'm not near a top expert, but maybe I will be able to give some points of view, trying to argue the argument. And that's fine. But the argument isn't like, this isn't nuclear physics kind of thing. You know, you don't have to keep track of a whole bunch of abstract ideas. I'm basically saying it's a push universe, okay, and that the push is made out of stuff. And you have to conserve the stuff that does the pushing. So it's a push universe, and there's conservation of push. So it's not that complicated an argument, that there isn't extra push somewhere. There's only a certain amount of push in the universe, and it just moves, pushing this, pushing that, push, push, push. It just moves to different locations, pushing different things. Okay. I guess I'm going to make on the website, I'll try to make a video series. It's just some of these ideas, if you're not willing to even say, well, maybe that's right, and go with it, for the sake of the argument, concede that as a possibility, and then say, oh yeah, I can see how that would connect to this, and explain that, and then it explains this and explains that. Well, you really can't see all those connections if I can't even get you to understand that push is elementally simple. Something just bangs into something. And push is elementally complicated. It's really hard to imagine how something over here could possibly pull something over there. Hitting it won't work. So what's it going to use? Some sort of magic force. All right, question. If I'm in space and I throw a 2-liter Coke bottle away from me at 1 mile an hour, do I receive the same thrust if I shoot a dime 2 grams away from me at 1,000 miles an hour? If so, isn't this proof against the kinetic energy formula? So I think it's a simple enough question. Is it the same thrust? Is the first question. So you should answer that one. Okay, to simplify the argument, it's already goddamn simple. Let's focus on pushing things. Heavy pushes light. So now you're just saying that we're back to the conversion argument. I'm clearly arguing that you can have a big M and a little v, and then you just have to convert the total amount of that mv. So you can make a little m, but it'll have a really big v because it has to be equal. And it's that simple. And I'm saying there's no experiment that's credible. There's no experiment showing it taking 4 times the fuel to go twice as fast. Okay, there's no experiment showing that MV not to work. All by itself, no squares needed. Newton, Descartes, and Galileo, again, got all their right answers, understanding it as MV, not MV squared. They understood that the mass was just as essential as the velocity. That's the total way you see how much total force something has, is you see how much total mass is it moving and how fast is it moving. Less mass, the force can move faster. More mass, it has to share the force like butter on a bread, and it has to spread it thinner. During the time of the push, so again, you're talking about how it got pushed. The simple question was, if I throw those 2 things out of the spaceship, who cares how I did it? There's a dime going 2,000 miles an hour. There's 2 liters of Coke going 1 mile an hour. That's what's leaving the spaceship. That was the question. All right. It takes a while. Well, I don't know. Does it really? You can see this, I did watch the bullet into a bullet experiment by Smarter Every Day, but I almost hate mentioning it's just that these are just such clickbait, and they try to say, this isn't a clickbait. Yeah, it is a clickbait. The whole way it's presented, the whole way it's done, it drags it out for no other purpose than to, intensify. But anyway, but incredible. The cameras have gotten incredible. So yeah, it must be a $30,000 camera because it's just incredible that you can actually videotape a bullet's travel. It's just amazing. Just the physics of that is just stunning. That we've had the technology to do that now. And what's it being wasted on? Show video. Let's blow something up. Let's not do a physics experiment, where we actually figure out where the momentum and the energy went. Let's not calculate an actual 4 times the energy, go twice as fast. Anyway, during the time of the push takes, it takes a while, whatever. Equal amounts of force F is applied. Well, it's obviously not equal. That's the whole point. It's being distributed either quickly or slowly. There's variable amounts of time depending on how big the object, how big the differential between the two objects are. Because the time really is just the conversion time. And the Newton's cradle kind of proves it. The Newton's cradle does this, okay, where this leaves essentially at the same rate. I mean, the pendulum doesn't lose a lot of time, okay, because the conversion is pretty one way. It doesn't, the force doesn't get interrupted. It doesn't have to negotiate with the other object and say, how much do you weigh, and all this kind of, no, it's automatic. It goes right in and it hits the side, essentially. So it goes in at the speed of sound inside the object, little tiny object, by the way. And so that's the only thing slowing it down is the speed of sound here. Otherwise, the swing is exactly the same speed. And it hits, the vibration goes right into the object. The object says, perfect. It's exactly the rate of force I need to accelerate. Your deceleration will perfectly match my acceleration, no problems. Obviously, with the heavier mass on one side, it has to be converted. The nickels have to be converted into quarters because this one can only handle quarters, that kind of thing. And the conversion time means vibrations back and forth inside the object to negotiate the transfer of the inconsistent denominations of the money. This one can only accept a certain acceleration for all of its elements, and this one has a different deceleration. The two don't match, and so that's why everything goes to shit. Okay, let's see. Equal amounts of force F is applied on the pusher and on the pushed for equal amounts of time. So that's not what Newton says. You can't say Newton said that when you bang uneven massed objects against each other that they stay in contact for the same amount of time. And no, he didn't do any of that. You probably agree, no I don't, okay, that the pushed equals lighter grains, velocity faster. Newton again, I believe. Yeah, Newton said, look, you want to go twice as fast, you just apply twice the force. You don't apply 4 times the force. So that's directly quotable out of Newton's explanation of the second law. His explanation of the second law contains the very statement. You want to go twice as fast, twice the force. You want to go 3 times as fast, 3 times the force. He's clearly seeing no correlation between twice as fast, 4 times the force. No correlation at all. He's basically saying force equals momentum, kind of clearly. You want twice the momentum? Put in twice the force, because, yeah, they're the same thing. All right. Thus, the pusher must move its own mass. I don't even know, can't even say much about that. Thus, the pusher must move its own mass. You're decelerating one object and accelerating the other object. That's what contact imposes. That's what friction does. Okay, you have motion, the other stuff isn't moving relative to you. You exchange motions with the object you're hitting. And that's it. You're just exchanging your state. One state is electrical. You could just think of it as an electrical state. And all you're doing is when you hit the other thing, you're exchanging your electrical state. It's attempting to become one electrical state. All right. Its hand, its spring, or whatever, okay, to the direction of the push. In this case of guns, no, there was no mention of guns, frankly. There was just a mention of a dime going 2,000 miles an hour and a 2-liter bottle going 1 mile an hour. It's the explosion that starts the moving to the direction of the bullet. So again, there's no gun. So, you've added stuff to this that you didn't need to add. Okay. And I mean, the question is right there. If I'm in space and I throw a 2-liter bottle out of the spaceship, I'm just throwing it. I'm taking a mass, giving it a velocity in a direction that I'm allowing to leave my spaceship. I have to have the equal and opposite reaction in the sense that I just gave away a bunch of energy going that way. So my total energy must contain less that way. So I end up going that way because I have less that way. All right. Here, the energy of the pusher that made the hand move is eventually transferred, ideal transfer, to the pushed object as kinetic energy. So what does that even mean? I mean, I'm clearly asking a simple question you won't even answer. Okay, does the spaceship turn? That's all. I have equal momentums coming out either side of the spaceship. Okay, I mean, I can go this way and I'm back to normal again. They're opposite forces, they're opposite interactions. Okay, there's not zero energy. I actually do go this way and then I go back. I mean, while Vm is conserved. I mean, you're saying both are conserved there. You're not making any sense. Here, the energy of the pusher that made the hand move is eventually transferred, ideal transfer, to the pushed object as kinetic energy. I don't know what that is. It's momentum, while the Vm is conserved. Yeah, so where does this squared term come from? Where you're telling me, okay, that there's some reason for me to believe that whatever kinetic energy is, that doesn't have to be conserved. That is, I don't have to have a cause for it. There doesn't have to be a creation force. Anyway, this should give an ideal why the dime gains more energy. So again, you're saying it has more energy. I don't give a fuck how it got it. I'm saying, does it have more energy? The simplest way to see if it has more energy is to ask the simple question, what happens to the object that produced it? This object produces a 2-liter Coke going that way, and it produces a dime going that way. The simple question is, you have 2,000 joules of energy ejected by kinetic energy formula this way, and you have 2 joules ejected that way. Does the spaceship turn? I mean, it's not a complicated question. Does it turn the spaceship? What I'm saying is momentum turns the spaceship, and that's a real indication that the truth is there is no kinetic energy. It is, in fact, a fable with almost zero, even slightly credible evidence in defense of it. I mean, it's so little evidence that you have that this kinetic energy crap exists. You have no experimental evidence showing it. You have no example of 4 times the fuel to go twice as fast. I mean, it's so obviously just a fable. Momentum works just fine. Momentum explains what happens to the spaceship. Momentum is real energy, and the real energy is those two things are the same thing. The flicked dime is the same as the, pushed 2 liters. The MVs match. Let's see if he actually answers the question. Okay, but let's see. I mean, it wasn't that, all this evasion. Anyway, this should give an idea why the dime gains more energy than the bottle. So there's first, we didn't even examine how these were produced, but I could argue I could produce them with a gun, okay, and that I could fire one and the other, okay, and out of the same explosion. And you'd have to explain how in one case the explosion produces 2,000 joules, in the other case it produces 2. That the explosion was completely uneven. And I could even go to what I've drawn it right on the board over and over. I mean, I hate to be so redundant, but it seems like people don't pay any attention at all. I can make a zip gun and shoot 2 bullets. Like having one explosion right here in the middle of a empty tube. And I have one explosion, not 2 explosions, not just one. And the bullets fly out. And the fact is they're going to fly out with 2,000 joules by your definition on each side. My definition will be 2. Okay, then I change the experiment and put a gun inside of a gun. Now I'm going to have 2 joules and 2 joules. Okay, momentum says still everything's just fine. 2, 2, 2, 2. Everything is the same momentum. The bullets have the same momentum as the recoiling guns. It's all okay. Your theory says one explosion creates 4,000 joules of energy and the other explosion creates 4. I'm saying there's no conservation of energy there at all. That's nonsensical. All right. I mean, whatever. So it gets the same. Okay, so here we go. So here's the word thrust anywhere. So we'll see. This should give an idea why the dime gains more energy. So again, I have no idea where the energy came from and why you say it has it. But whatever. It has the same momentum. Then the bottle, even though you get the same thrust. So you answered the question. Okay, you're saying it's the same thrust. So you're saying your kinetic energy formula says you have generated 2,000 joules in one direction. You have generated 2 joules in the other direction. If they were photons, you'd certainly be able to understand that can't be right. If they were heat, okay, I can convert joules into watts. You've produced 2,000 watts one direction, 2 watts the other direction. It's impossible for you to, reasonably argue that wouldn't turn a spaceship. Of course it would turn it. So you can't make this statement and say that makes sense to you. How could it possibly make sense to you? I can directly convert a joule into a watt. You're telling me I can shoot 2,000 watts of heat one direction. I can shoot 2 watts of heat in the other direction, and somehow I'm going to not be. The two will equal each other. 2 watts equals 2,000 watts. No, it doesn't work, but clearly momentum does. Whatever. Even though you get the same thrust. So it does. So he's saying there's the same thrust in the thing with 1,000 times more joules of energy, 1,000 times more watts, and it's the same thrust. Obviously, that is not acceptable reasoning. You can't go with that as an answer because it's just too stupid. Okay, you use more energy to move things. Well, says you, and if I used more energy to move them, then I would have to obey the equal and opposite reaction laws, and the ship would have to turn. So you can't have it both ways. You can't say you use more energy to generate the objects, because using more energy, the spaceship would see. This is easier to understand when you make the masses different, even larger. I mean, what the fuck are you saying? We're at 1,000 times difference in their mass. Why do I need to make it any larger? I mean, that would be fucktarded. I already have a gigantic differential. I mean, it's a mouse and an elephant, for fuck's sake. If you want to get a good acceleration in space, would you rather push a dime or a spaceship? It doesn't matter. You're only going to get as much energy as mass you moved. So that's it. There's no other rule in space. It's just about how heavy is it will tell you how fast you can move it. Period. The end. That's the whole point of the whole question. I mean, it's just, if you want to get good acceleration in space, would you rather push a dime or a spaceship? It doesn't matter. The movie Gravity, right, with the chick and the whole thing, they'd have one scene where she's using the fire extinguisher, right? I mean, so it's a kind of a cliche way of understanding that all she has to do is change the direction of the nozzle, and she changes which way she gets pushed. But she finally runs out of fire extinguisher, and what does she do? She throws the whole fire extinguisher, all right, pointing out that that's just as good a way of producing a mass and a velocity and giving it away as any other way. You just threw a heavy object, made it go in space with mass and velocity. It now carries the energy you gave away. You had to give away this way, the way you threw it, okay? And now you're stuck with a differential because now you gave away, okay, energy in that direction. You now have extra energy in the other direction. You have more stuff inside of you going the other way because you gave away that way. I mean, it's so obvious. Okay, so he edits. This was not a great answer. Yeah, it really wasn't. Wasn't even close to answering the basic question. So you answered the question by saying you are correct. Kinetic energy is absolutely useless in this scenario. Momentum will decide where the spaceship moves. So that should be your answer. If you're going to say the spaceship doesn't change its orientation, that the two things are the same thrust, then you have to concede that, well, yes, it's true that when I isolate everything in an experiment, I do it in space, guess what? Kinetic energy doesn't show up at all. It's not at the party. Try to make it slightly better. It explained more why the bullet gains more energy than the gun. Well, it doesn't explain that either, because we know that's an explosion that is symmetrical. And there's no good reason why you can make this argument. The bullet's explosion is many times smaller, faster particles. They're going to hit these big things, the bullet and the gun, and there really isn't enough time at the speed they're moving for them to bounce around and do a bunch of extra pushing. So basically the gun's going to get pushed with one half of the explosion, the bullet's going to get pushed by the other half of the explosion, and that's exactly what we see. We see the same momentum. Too confusing. In the case of the dime versus the bottle, you get the same thrust. You get the same useful event. You get the same substance of movement. Again, quantity of motion is completely in control, and there's no sign of the fable. There's no sign of the gremlin, okay, of mv squared. There's no sign it's doing anything, or it did anything, or it has any function. There's every sign it's a fable. But accelerating the dime to 1,000 miles per hour needs more energy. So that you will not demonstrate with any experiment. So that won't even come close to being the truth. You won't show it. You won't make that in any way a fact. You're just saying it. But accelerating the dime to 1,000 miles an hour needs more energy. Where? Where did you prove that? Oh, that's right, you didn't. You don't believe this? Yes, that's right. I don't believe that at all. But maybe next time answer will have something to think about. You don't believe this, but maybe the next answer have something to think about. So we just evaded it pretty much. But whatever, fine. Okay. So garbage, frankly, as an answer. The simple truth is you have to concede, well, apparently kinetic energy, the extra watts of energy that are going one way and the watts going the other way, apparently it doesn't make any difference. Watts aren't important. No, the point is that there is no wattage. You're just making up fake numbers. You gave the bullet an insane amount of energy it doesn't have. There are no 1,000 more watts. It doesn't have 1,000 watts. It won't move 1,000 watts of particles in the universe. That's the fact. Because all it is momentum. All right, question. Is there any physical evidence defending the kinetic energy theorem? Yes. It's, what we have are, well, we have some Brozosian nonsense, but we have dropping round things into clay, and we have the fact that it's 4 times the height to go twice the velocity, which, you know, it's pretty easy to understand when you mean, well, if it's going twice the velocity, it's going through the time-dependent force at twice the speed. And then you have the fact that stuff rolls further. And I've already explained that's simply because there's less friction when you're going faster. You have less contact with the surface, you can lose less energy, okay, because you don't have the same contact with the surface. You need contact with the surface to lose energy. You're not losing the same amount of energy per foot, obviously, when you're going faster. All right, the theory says an 8-pound bowling ball will produce twice as much energy as a 16-pound ball thrown with the same effort. No pro bowler can make a lighter ball work. Why? Okay, simple enough. Some home video level evidence has been presented to you. I don't know what that means. I didn't see any of that. Whatever. But you don't accept any of them. Well, what does that have to do with this simple point? Do you claim that the 8-pound ball has more energy or not? You're saying the 8-pound ball has more joules of energy, right? The 8-pound ball going twice as fast has more energy than the 16-pound ball going half as fast. You claim it has more energy. There's a simple test, okay, where people try to knock things down with the thing's energy. The testers, the professional testers, can't make the 8-pound ball do this twice as much thing. They can't get twice as many pins to fall down. What do you have to say about that? Nothing. The theory says okay, so let's see. You don't accept any of them. That's fine. Well, apparently it's not fine. You're somehow implying that I'm supposed to accept these garbage experiments, frankly, that always have obvious flaws. I don't know how these equations are used in real life. Well, this isn't complicated. I mean, you're just saying, does momentum work? Does momentum knock pins down, or does kinetic energy knock pins down? I think the simple proof of the experiment that's been conducted by professional bowlers is that momentum knocks pins down, and that there is no advantage to using the 8-pound ball going twice as fast. I assume they are. All right. I don't know how these equations are used in real life. I assume they are. It's a fact you're saying the physics has this character. You're saying it has this ability. All right? And I'm asking you to simply demonstrate this ability. Show me where the gremlins actually do work. So here the gremlins are supposed to be able to knock down twice the pins. The experiment shows, no, it doesn't work that way. The 8-pound ball does not transfer more wattage, more pins moving. It doesn't make more heat. If you did the experiment making heat, you're not going to make more heat with the 16-pound ball going 8 than the 8 going 16, or vice versa. They're going to make the same amount of heat. But I want to make another point. Well, so you want to, just, again, not answer the question. Okay, in these mechanical questions, the definition of work, so this is more, why would I bother with this silly definition? It's a silly definition, frankly. Forces are a pressure applied over a time, and that's what they are. They're time dependent, they're not distance dependent. So it's just crap, frankly. Okay, is the interesting one. Yeah, well, why don't you look up where they invented it in like 1840, and they just invented it. All of a sudden, one day it didn't exist, and the next day, all of a sudden, everybody knew the new work equation. All right, you disagree with this. And why did it exist? Merely because of the kinetic energy equation. They had to create a work equation that fit the kinetic energy equation. The two had to be compatible. Duh. If they tried to be compatible with momentum, then it would be work equals force times time. But the thing is, if the object to which you are applying the force does not move, then it doesn't get the energy. That's the thing. The energy is going to end up reflecting. But anyway, let's continue. Or vibrating. Think of a man holding a weight in the air. So again, this is a bad example because your silly physics says he's not doing any work. And that's absolutely silly. I mean, it's so silly. It's just so... Why bother having physics if you can't accurately describe what it's like to hold up 100 pounds against gravity? And you're going to say something absolutely silly like, I'm holding 100 pounds against gravity, and you're going to say, I'm not doing any work. I mean, it's so fucking stupid. And you're proud of that physics? You'll argue in defense of that physics? I mean, it's just so inaccurate. It's such an incomplete theory. I mean, to argue you're not doing any work is an incomplete theory. Oh, God. The status of the weight is not changing in any interesting way. Yeah, in any way you can see, but obviously your body is, and the weight is in fact jiggling in gravity, just as we are when we're sitting on the ground. That's why the ground constantly pushes back. It's because we're constantly pushing into it. You can't, why would I still feel the weight of gravity if I wasn't in fact absolutely still pushing into the earth all the time, constantly? It does not drop harder or longer the longer you hold it. Yeah, that's the work isn't going into the weight. The work is going into the ground, and clearly it has to go through you, and you're all rubbery. So you're wobbling it all over the place and doing lots of moving it up and down against gravity. Only when the object moves can the force be transferred to the object as energy. So that's the way you're looking at it. I've sort of pointed it out. The thing collecting the energy from gravity is the weight. The energy goes into the weight. If you don't allow the weight to move, then it goes into the force stopping it from moving. It goes into the entity that's stopping it from moving. Clearly it goes into you. And then you transfer it into the ground. I mean, it's not that complicated. Yes, if we were made out of rigid steel or something, you could say the steel's not doing any work, but we know the steel is stressed. If I compress a spring with a piece of something and the something is holding against the spring, you know that metal is stressed. You know it's not just happy, that everything is just fine, because you know that you can push a tiny bit more and break it. So you know you've stressed it. The stress has to be called work. This is why W equals FD makes sense. So it doesn't make sense to me, and I don't see how you possibly made sense out of it by talking about the distance again, because clearly a lot of work is being done and no distance is being covered. You're not, traveling any distance, but you certainly are. Again, the whole point would be to argue is that, yes, there is actually distance involved. But it's not at a 2-to-1 relationship. All distances is not movement in gravity or rolling on the ground. All distances in gravitationally imposed friction. If you're allowing gravity to be the cause of your contact, then obviously it's going to be by this 4-to-2 relationship rather than the 2-to-1 relationship that the lever demonstrates, for example, that it converts it to. So again, it's why would you think the distance is proof of the work when I can simply say to you, do you believe, so the other question would be, do you believe that friction changes with velocity? So the amount of friction you have rolling, you'll create more heat in the ground the slower you're going. So the slower you're going, the more energy you'll put into the ground per foot, and the faster you're going, the less energy you'll put into the ground per foot. Do you understand that conceptually? And if you do concede that, then you have to concede that yes, the distance would not be directly correlated to the energy, because the distance will change depending on how much velocity there is. I'll be taking less energy from the object. It makes sense. So it doesn't make sense. And can energy logically follow? So there's no logic to it at all. I'm saying the two most fundamental experiments, dropping something, it's only in the gravity 2 units longer. 4 times the height, twice the time. 9.8 meters per second. You can only get to 9.8 meters. You only have 19.6 velocity. It clearly matches. You only got 2 units of gravity because you only have 2 units of velocity. You only have 2 units of 9.8. How the fuck can you argue that you have any more than that? Twice the velocity hitting the ground is going to be twice the weight hitting the ground. You're only going to do twice the damage. You're not going to do 4 times the damage. What are your thoughts? I've already made them and said them hundreds of times now, and you just ignore them. It's a time-dependent force, gravity. If it's 2 seconds free-falling, how can I say that's 4 units of energy? Why would I say that? It's not 4 units of energy. It's only 2. If you accept this, unlikely I know, I don't even know what I was supposed to accept. It doesn't even make sense. You're not explaining how momentum completely fails to get the right answer. No, you're not going to explain it at all. The bowling balls will make more sense to you. In what way will it ever make more sense to me? In what way can it ever make more sense to me? Why should I ever think twice the velocity is 4 times anything? Why? What's the example? 2 men hit me at, let's see, I got to do it the right way, right? 25 miles an hour, or 1 man hits me at 50 miles an hour. Why the hell should I see a difference? Why? Why should I think one is twice as damaging? The one guy going faster has twice the energy. Why? All right, the man holding a weight uses energy for purely human physiological reasons. I don't even know how this even makes any sense. The fact that he's using energy means he's doing work. It's just too stupid. Maintaining muscle tension requires energy. An ideal spring does not get tired. The things holding it can. So again, more bullshit. And how do you know? I mean, how many billions of years did you compress a spring? So there are some fatigues that take place over time. Depending on what I make the spring out of, I could, frankly, cause it to permanently compress. I mean, some things are elastic in a very slow way. Some elastics, you could pull on them, and it would take 3 months for them to fully restore to their original condition. 3 months, whatever. So another non-answer to the simple question: if it has twice the energy, why can't bowlers make twice the energy work? Why can't they extract any of that? If you shoot 2 objects with the inverse velocity to mass ratios, for example, 10 to 5, 5 to 10, into gravity, your formula says one object will have twice as much energy. Okay, so they say the 5-ton train going 10 miles an hour has twice the energy of a 10-ton train going 5. That could have 2 10-ton trains going 5 on one side of the tug of war. And only then could I overcome the power of the 5-ton train going 10. It's too silly. Anyway, as the other at liftoff, if I let the objects fall on an ideal spring, they will be recorded to impress the same pressure, the same joules of energy. How do you reconcile the fact with your theory? 4 times the height gets you only twice the weight. That's the fact. Or do you dispute the fact? I dispute the fact. So he says it doesn't happen. Okay, that it's not 4 times the height, twice the weight. I predict that the faster will cause more compression. So go ahead and show it. Some crude evidence has been showed to you, I think. No, they didn't drop anything on a spring and show how much spring compression there is. I did that one. Okay, that's this one. Yeah. Well, I think this spar is trying to do them, but I mean, he's doing them with that bizarre scale, the upside down scale. Okay, that you have to move the entire mass of the scale. So yeah, that's not an ideal experiment. The mathematical reasoning would combine the Hooke's law to the idea of work equals force times distance. Well, you can't combine those two things. I'm just saying that's idiotic, in the sense that the distance of the compression is only twice. It's twice the energy. So how does the work equation save you here? The spring isn't showing 4 times the compression. So I don't know how you convolute that answer. So I guess I should go look and see what questions he didn't answer, because those are only 3 of the questions. It's past my bedtime and I'm way too tired to write this. I hope there isn't too many mistakes. Editorial note might follow. What needs to follow is one of you people needs to learn how to draw and use a video camera. I just don't understand why you can't, none of you can interact in a scientific manner of doing body diagrams. You know, diagram the mechanisms of where the forces are coming from and how these interactions happen. How, like, diagram an 8-pound ball going twice as fast as a 16-pound ball, and then explain how the energy goes into each pin it hits. Because I've already done that, and clearly what the graphs show is that yes, the 8-pound ball will create higher velocity pins in the beginning, but as the ball travels, the 16-pound ball will start making the higher velocity pins at the lower speeds. The 8-pound ball wins the contest in the beginning, but the 16-pound ball wins at the end, and it ends up being the same volume of pin movement. There isn't twice as much energy in the 8-pound ball. It will not create atoms moving. It will not create twice as many atoms moving twice the velocity, or vice versa. It won't be able to move more matter in the universe. They will both move the same number of electrons in total. If you can convert the energy into quanta, they have the same quanta of potential to move quanta. Alright, so yeah, that's probably enough of a video and such. Yeah, I think that's enough. Alright, disappointing. That's, you know, all you can say, but whatever. It just is curious. I mean, you know, there's got to be 10 people who are rather aggressively arguing I'm wrong, and not one of the 10 people can make counter arguments relevant to the theoretical arguments I'm making in these videos over and over again. I mean, they could just draw. Let's just do one of the examples, just so there's something, some fodder here, where I'll point out the evasion, where they just are evading the fucking arguments made, just saying I'm not going to deal with that argument because I don't have an answer to it. That's the basic truth. They can't answer the questions. They can't answer the apparent paradoxes their theory creates. Alright, so it's a really simple experiment, right? I mean, the simple idea. Okay, I have a zip gun, is what these are called. I have the same explosion. I'm going to do the same experiment. Alright, and I do the experiment with little light bullets. Okay, so these bullets weigh, they're going to be 1,000 times difference in their masses. Okay, so these bullets are like, whatever, 1 ounce bullets. I have the explosion, I shoot the bullets, and you know, we can calculate, or we could just say, we could just measure the masses and velocities of the bullets. Okay, they're going to have a certain, these are going to have a very high velocity, very small mass. Okay, and that's what we're going to get. Okay, high velocity, small mass. Alright, do the same experiment. Alright. And this time I just make the masses equal to the recoiling gun. So this side is, you know, now the masses are heavy, 1,000 times heavier. Okay, masses. And I have the same exact explosive, and I shoot them out, and I'm going to get big M, okay, and little v. Okay, and your theory says, okay, that in this case I created 1,000 joules here. Okay, and in this case, the other way around. This is 1,000 joules. This is only 1 joule, 1 watt. So I have 1,000 watts, 1,000, 1 watt, 1,000 here. Okay, 1 here. So this experiment, same explosion. This explosion creates 2,000, okay, watts. I mean, you have to agree that a watt is a joule, right? So I can do this. This is completely legitimate to understand that the joules do add up to basically heat units. All right, and then the other experiment produces 2. Just 2 joules, 2 watts. Okay, that's it. So you're saying that this makes sense to you, that the same exact explosion created this insanely different differential in the amount of energy in the universe. That we have you know, we have 1998 energy units that were dissipated in some other form, that are disappeared in some other way. So this is just the gun inside the gun. You know, I don't want to confuse you. This is just saying I can put a gun barrel inside another gun, and all I'm going to get is 2 recoils. I'm going to get a recoil this way and a recoil this way. So the recoil energy is the only motion I'm going to get out of the same explosion. So again, how is this differential possible, and how can you possibly explain it as being real? So momentum says everything is fine. I have 2 here, 2 here, 2 here, 2 here. Momentum says everything worked just the way it's supposed to work. Everything's sensible and rational. Kinetic energy says this loop-de-doo nonsense that somehow this experiment is, the explosion is 2,000, produces 2,000 joules of energy, and here the explosion doesn't do anything at all, or barely anything. Explain. Please, someone, explain where what I said somewhere is wrong, where there's a gigantic error in the logic and not explaining what actually happens, where I falsified the example of what would be. Explain how it wouldn't be, that it wouldn't happen that way. All right. So that'll do, pig and such. So till the next time, this has been another DraftPhysics.com video presentation to a world completely uninterested in anything called the truth, which is just so obvious. They just don't want to believe. They don't want to live in reality. They want to live in, I don't know why, Gremlindia, Pixitosia. They want to live in a frickin' fake, phony fairyland, fable land.